Hi, Stu Schwartz, MasterMathMentor.com. This is video BC Non-Essential 3a. The topic is Integration with Partial Fractions Advanced, and it covers the BC manuals, pages 149 and 150. As a review, we learned how to take the integral of an expression in the form of a polynomial degree less than or equal to n minus 1 over the distinct factors x minus a, x minus b, x minus n dx. We broke these up using partial fractions and the Heaviside technique to create the integral of a over x minus a plus b over x minus b plus plus n over x minus n dx. And the integration was simple, getting a natural log absolute value of x minus a plus b natural log absolute value of x minus b plus plus n natural log absolute value x minus n plus a constant. So to integrate 1 over x squared minus 1, we can write this as the integral of 1 over x plus 1 times x minus 1 dx. And since these have unique factors in the denominator, then we can integrate this using the Heaviside technique, which is not shown. The same holds for the integral of x over x squared minus 1. We can write that as the integral of x over x plus 1, x minus 1, and again we can use the Heaviside technique. However, with the integral of x squared over x squared minus 1 dx, since the numerator has a polynomial which has the same degree as the denominator, we will do long division, dividing x squared minus 1 into x squared, and we get 1 plus 1 over x squared minus 1. So the integral of x squared over x squared minus 1 dx is the integral of 1 plus 1 over x squared minus 1 dx. Again, we could break this into two integrals, integrating 1, which is easy, and we just showed that we can integrate 1 over x squared minus 1 using Heaviside. Suppose we were asked to integrate x over x squared minus 2x plus 1 dx. We start with u substitution, where u is equal to x squared minus 2x plus 1, and therefore du is equal to 2x minus 2 dx. And there's no way we can pull this off. So u substitution does not work. We can factor the denominator and write this as the integral of x over x minus 1 quantity squared, which is the integral of x over x minus 1 times x minus 1 dx. But our Heaviside method will not work here because we do not have unique factors in the denominator. We have a repeating factor. However, we can still create partial fractions. When we have an integral in the form of a polynomial degree less than or equal to 1 over the repeating factor x minus a times x minus a dx, we can write this as the integral of a over x minus a plus b over x minus a quantity squared dx. And once we know what capital A and capital B are, we can integrate each piece. The first piece by using logs, the second piece by the power rule, getting a natural log absolute value of x minus a minus b over x minus a plus a constant. Let's see how this works on this problem. So let's create the partial fractions. We write x over x minus 1 squared as a over x minus 1 plus b over x minus 1 squared. The trick of this is to multiply out by the highest power of our x minus 1, which is x minus 1 squared. So we multiply both sides by x minus 1 quantity squared, and we end up getting x is equal to a times x minus 1 plus b. To find b, we will let x be the number that will cancel out the a. In this case, x is 1. So we get 1 is equal to a times 0 plus b, and therefore b is equal to 1. To find a, we will let x be any number other than, in this case, 1, because we want to have an a in our expression. We'll let x equal 0. So we get 0 is equal to a times negative 1 plus 1, and therefore a is also equal to 1. So the integral of x over x minus 1 quantity squared dx can be written as the integral of 1 over x minus 1 plus 1 over x minus 1 squared dx. And as we've said, the first integral will simply be a natural log, and the second will use the power rule. Final answer is natural log absolute value of x minus 1 minus 1 over x minus 1 plus c. In number 2, we're asked to integrate 4x plus 7 all over x squared plus 4x plus 4 dx. It is clear that u substitution will not work, because if u were the denominator, then du would equal 2x plus 4 dx, and we cannot pull that off. We also cannot do this by our traditional Heaviside method, as the denominator factors into x plus 2 quantity squared, which will have a repeating factor. So we write 4x plus 7 over x squared plus 4x plus 4 with partial fractions as a over x plus 2 plus b over x plus 2 quantity squared. Multiplying out by x plus 2 quantity squared, we get 4x plus 7 is equal to a quantity x plus 2 plus b. Our first step is to let x equal to negative 2, and that will mean that b will equal negative 1. We then let x be any number other than negative 2. We'll let x equal 0, and we get 7 equals 2a minus 1, and therefore a is equal to 4. So we're really being asked to integrate 4 over x plus 2 minus 1 over x plus 2 quantity squared dx. And this turns out to be 4 natural log absolute value of x plus 2 plus 1 over x plus 2 plus c. In number 3, we're asked to integrate 4 over x cubed plus x squared dx. It is clear that u substitution will not work, as if we let u equal x cubed plus x squared, du is equal to 3x squared plus 2x dx, and there's no way we can pull that off. We can factor this, but when we factor the denominator, we get x squared times x plus 1, and we have therefore a repeating factor. So we write 4 over x cubed plus x squared as 4 over x squared quantity x plus 1, which is a over x plus b over x squared plus c over x plus 1, writing it with partial fractions. Multiplying every term by x squared quantity x plus 1, we get 4 equals ax quantity x plus 1 plus b quantity x plus 1 plus c x squared. First job, we will let x equal negative 1, and from there we get c is equal to 4. We then let x equal 0, and from there we get b is equal to 4 as well. We now let x be any value other than 0 and negative 1. We'll let it be 1, and we get 4 equals 2a plus 8 plus 4, and therefore a is equal to negative 4. And therefore our integral of negative 4 over x plus 4 over x squared plus 4 over x plus 1 turns out to be 4 natural log absolute value of x plus 1 minus 4 natural log absolute value of x minus 4 over x plus c. Number 4, the integral of 4 over x cubed plus 4x dx, we throw a twist. Obviously, u substitution will not work, and our normal partial fractions techniques will not work because the denominator factors into x times x squared plus 4, and we need to have linear factors in order to use the Heaviside method. So we will write this with partial fractions as 4 over x times x squared plus 4 can be written as a over x plus bx plus c over x squared plus 4. Whenever we have a non-factorable polynomial, we will write this as the numerator being bx plus c. Again, our first job is to multiply all terms by x quantity x squared plus 4. And when we do that, we get 4 is equal to a quantity x squared plus 4 plus x quantity bx plus c. We will let x equal 0 to eliminate the b and the c, and we get 4a is equal to 4 and a is equal to 1. So plugging in our a, we get 4 equals x squared plus 4 plus x quantity bx plus c. And from there, that gives us 0 is equal to x squared plus x quantity bx plus c. At this point, we set up two values of x that will give us two equations involving b and c, and can therefore be solved for b and c. So we'll let x equal 1, and we get 0 is equal to 1 plus b plus c. If x equals negative 1, then 0 is equal to 1 plus b minus c. Adding the two equations together, we get 0 is equal to 2 plus 2b. b equals negative 1, and therefore c is equal to 0. So therefore, we really are integrating the expression 1 over x minus x over x squared plus 4 dx. And this turns out to be the natural log absolute value of x minus 1/2 natural log absolute value of x squared plus 4 plus c. Number 5 reads the integral of x minus 4 over x cubed plus 4x dx. Again, u substitution will not work, and we cannot do this by the traditional partial fractions technique because the denominator factors into x quantity x squared plus 4, which are not all linear factors. So we write x minus 4 over x squared plus 4 as a over x plus bx plus c over x squared plus 4. We will multiply both sides by quantity x squared plus 4, and we end up getting x minus 4 is equal to a quantity x squared plus 4 plus x quantity bx plus c. Letting x equal 0, we get negative 4 is equal to 4a, and a is equal to negative 1. So our equation now reads x minus 4 is equal to negative quantity x squared plus 4 plus x quantity bx plus c. Our technique remains the same. We will use two different values of x to generate two equations involving b and c. So if x is equal to, for instance, negative 1, we get negative 3 equals negative 5 plus b plus c, getting b plus c is equal to 2. If x is equal to negative 1, we get negative 5 equals negative 5 plus b minus c, and this gives us b minus c is equal to 0. Adding the two equations together, we get 2b is equal to 2, and b is equal to 1, and therefore subsequently c is equal to 1 as well. So our integral of x minus 4 over x cubed plus 4x dx can be written as the integral of negative 1 over x plus 1 over x squared plus 4 dx. We will break this up into three integrals and write this as the integral of negative 1 over x plus the x over x squared plus 4 plus 1 over x squared plus 4. And each of these uses slightly different technique. The first integral is negative natural log absolute value of x. The second is 1/2 the natural log absolute value of x squared plus 4. And the third is 1/2 the inverse tangent of x over 2 plus c. These problems can get tough. You need to work very clearly and slowly. For instance, on number 6, the integral of x squared minus x plus 1 over x to the 4th minus x to the 3rd plus x squared minus x dx is very clear that substitution is not going to work. And if we cannot factor the bottom into linear factors, which we cannot, then the only way to do this is by the technique we've just shown. We start by factoring out the denominator and writing it as x cubed quantity x minus 1 plus x quantity x minus 1. And we can now factor out an x minus 1, so our expression is x squared minus x plus 1 over x quantity x minus 1 x squared plus 1. We take this expression and write this as a over x plus b over x minus 1 plus cx plus d over x squared plus 1 as our partial fractions. And now multiply both sides of our equation by quantity x, x minus 1, x squared plus 1. This gives x squared minus x plus 1 equals a quantity x minus 1, quantity x squared plus 1, plus bx quantity x squared plus 1, plus x quantity x minus 1, quantity cx plus d. We start by letting x equal to 0. And that gives us a very simple a equals -1. We also let x equal to 1, and from there we'll get 1 equals 2b, and b is equal to 1/2. Rewriting our equation, we get x squared minus x plus 1 equals negative quantity x minus 1, x squared plus 1, plus 1/2 x quantity x squared plus 1, plus x quantity x minus 1 times cx plus d. We need two equations now to solve for c and d. So we will let x equals 2 and -2. When x equals 2, we will get 3 equals -5 plus 5 plus 2 quantity 2c plus d. And therefore, 3 is equal to 4c plus 2d. When x equals -2, we get 7 equals 15 minus 5 plus 6 quantity -2c plus d. And this gives -3 is equal to -12c plus 6d. We will multiply the top equation by 3, and getting 9 is equal to 12c plus 6d. And adding the two equations together, we get 12d is equal to 6. And therefore d is equal to 1/2, and from there we can get that c is equal to 1/2 as well. So our expression, the integral of x squared minus x plus 1 over x to the 4th minus x to the 3rd plus x squared minus x dx, can be written with our partial fractions and our values of a through d plugged in as the integral of -1 over x plus 1 over 2 quantity x minus 1 plus 1/2 x plus 1/2 over x squared plus 1 dx. The last fraction can be split into two fractions. 1/2 quantity x times x squared plus over x squared plus 1 plus 1/2 times 1 over x squared plus 1. The third fraction, in preparation for some substitution, can be written as 1/4 times 2x over x squared plus 1. So now every expression can be integrated. We get negative natural log absolute value of x plus 1/2 natural log absolute value of x minus 1 plus 1/4 natural log absolute value of x squared plus 1 plus 1/2 inverse tangent of x plus c. There are techniques to solve integration problems with repeated quadratic factors in the denominator, but they are quite tedious, and typically if you need to perform such integration, using a computer algebra system is much more convenient.